date is November 9th, 2025. For months, astronomers have monitored the strange interstellar traveller known as 3I Atlas, a faint, elongated object first catalogued years ago after crossing deep space trajectories that no comet or asteroid should have followed. It had become one of the most studied bodies of the decade, a scientific touchstone for how matter behaves between stars. But now, a quiet series of observations from multiple observatories has begun to tell a different story, one that doesn't align with the object we thought we knew. At first, the changes were subtle, a slight deviation in motion, a faint shift in reflected light. Data discrepancies were dismissed as calibration errors, routine noise in the signal. Yet, over the past several weeks, those anomalies have multiplied, converging into a single, uncomfortable realization. The 3I Atlas, currently being tracked by ground-based arrays and orbital telescopes, may not be the same body that entered our system. Something fundamental has changed. Its trajectory no longer conforms to expected gravitational models. Its spectrum shows chemical traces that were never part of its initial signature. Its rotation rate, once steady, now fluctuates unpredictably, as if the object itself is losing coherence or transforming in real time. Teams across Europe, South America, and the Pacific are quietly comparing notes. None of them are willing to make public claims, but their internal communications reveal the same pattern. The data fits nothing known. No natural body should alter its mass distribution, composition, and luminosity so dramatically without an obvious external cause. Some suspect a breakup, a slow disintegration triggered by stress, perhaps by a close pass with a planetary field or residual heat from its passage near the Sun. Others think what we're seeing is a data mirage, interference from cosmic rays, lensing distortions, or even computational overlap between distinct objects in similar orbits. Yet, even after these variables are accounted for, the mystery deepens. The numbers still do not match. What remains is a question that feels less astronomical and more existential. If the entity we're now observing is not the same as the one we catalogued, where did the original go? Did it fragment? Did it transform? Or was it never a single object to begin with? No one is ready to say the words out loud. Not yet. But across the quiet network of observatories feeding nightly data streams to the International Astronomical Union, there's a growing unease. The object known as 3I Atlas has begun to defy its own identity. And tonight, under clear skies over both hemispheres, a faint trace of its light drifts again across sensor grids. Inconsistent, unpredictable, but still there. Whatever 3I Atlas has become, it is moving differently now. The investigation begins with its path, the one feature that should have remained constant but no longer does. For months, the projected trajectory of 3I Atlas had been considered one of the few stable aspects of its observation profile. A path plotted with precision across countless datasets. It was supposed to be reliable, a mathematical backbone against which every other measurement could be compared. But that confidence is now unravelling. When the first discrepancies appeared, they were measured in fractions of arcseconds, easily dismissed as noise. A few degrees of deviation here, a few seconds of timing drift there. Yet by late October, the pattern had hardened into something undeniable. The object was no longer where it should have been. Telescopes in Chile, Japan, and Hawaii began logging coordinates that placed 3I Atlas slightly ahead of its expected position, and then, suddenly, behind it. The shifts weren't consistent with natural perturbations from known gravitational fields. In celestial mechanics, such irregularities often suggest mass redistribution or fragmentation. If a body splits or ejects material, its centre of mass shifts, changing its path subtly but measurably. That seemed plausible until analysts calculated the scale of deviation. To explain it through conventional physics would require a loss or gain of several million metric tons of material, yet no corresponding debris trail had been detected. The object simply moved as if nudged by an unseen hand. Some began speculating about non-gravitational acceleration, similar to the tiny forces experienced by comets when sublimating ice releases jets of vapour. But at the current distance of 3I Atlas, temperatures are far too low for such activity. Moreover, its spectrum no longer displays the water or carbon signatures that such jets would produce. If outgassing were responsible, the chemical fingerprints would be obvious. They aren't. This left scientists in an uneasy gap between possibilities. Either the data was wrong, which multiple independent observatories now refuted, or something was actively altering the object's motion. For context, interstellar objects are not new to astronomy. Before 3i Atlas, there was Oumuamua, the first confirmed visitor from beyond the solar system. It too displayed anomalous acceleration that couldn't be easily explained by conventional models. But 3i Atlas was supposed to be different. Larger, colder, more stable, a control case of sorts. And now it was breaking that expectation in almost the same way, though on a much more dramatic scale. Deep space radar studies attempted to reconcile the deviation by constructing three-dimensional simulations of the object's path over the last 6 months. These reconstructions failed to align. The more the data was refined, the less coherent the orbit became. What had once been a predictable arc now twisted into something erratic, bending ever so slightly toward a region of the outer system where no major gravitational body exists. The change is not random. It appears to follow a rhythm, a recurring interval of deviation that repeats every 41 hours. That interval corresponds to no known resonance with nearby planets or asteroids. Instead, it resembles a controlled adjustment, an oscillation, as if the object is responding to an internal mechanism or to an external signal we cannot detect. There is no confirmed cause for this pattern. Every known physical explanation either contradicts observation or requires forces that, by all present measurements, do not exist in that region of space. As the anomaly grew, teams began to reprocess old data, stretching back to the first detections of 3i Atlas. What they found was troubling. The object's early trajectory data, when recalculated using the new deviations, produced a line that no longer intersected its original inbound path. In other words, if we trace 3i Atlas backward using today's behaviour, it would not have arrived from the same direction. The path's trajectory diverges, implying that somehow the object's entire motion history has shifted. That should be impossible. Space does not rewrite itself retroactively. Yet this is precisely what the numbers suggest. The recorded positions from earlier this year now fit a different orbital model than the one used at the time. It's as if the object we are tracking today emerged from a slightly displaced origin point, an offset reality where its journey was similar but not identical. Astrophysicists call this kind of shift a temporal divergence, though the term usually applies to data inconsistencies, not to physical bodies. Still, the implication lingers. If the mathematics now describe a different path, and the current data confirms a different object, then the conclusion becomes increasingly difficult to ignore. The object known as 3i Atlas may no longer be following its own history. But changes in movement rarely occur alone. If motion diverges, composition often follows, and so the next set of observations turn toward its light, the spectrum that reveals the true nature of its surface, and perhaps what might have changed within. Spectroscopy is often called the fingerprinting of the universe, a way to identify, with near certainty, the elemental composition of distant bodies through the analysis of light. Every atom absorbs and emits specific wavelengths, leaving behind a pattern of lines that, when decoded, tell a story about what an object is made of. For years, the spectral profile of 3i Atlas was considered routine, a combination of silicate minerals, trace metals, and carbon-based compounds typical of long-dormant cometary bodies. But this month, those fingerprints began to blur. When data from the Keck Observatory in Hawaii was compared with readings from the European Southern Observatory, analysts noticed something small but impossible to ignore. Several absorption lines that once indicated the presence of magnesium and iron oxides had shifted. The displacement was subtle, a few angstroms, just enough to fall outside instrumental error. That shift alone could mean many things: contamination in the sensor array, a calibration fault, or even atmospheric interference. But subsequent scans ruled all those out. The new readings pointed towards something far stranger, the possible introduction of a new spectral component. A reflective pattern appeared around the near-infrared range, consistent not with natural rock or ice, but with alloyed metals. The ratio between reflection and absorption suggested a surface that was, at least in part, more uniform than any known natural process could produce. It wasn't polished, but organized, structured at a microscopic level in a way that resisted randomness. When astronomers speak of structure and reflectivity, they mean coherence, an alignment of grains or particles that interacts with light in a predictable artificial manner. To observe this in an object drifting millions of kilometers from the nearest planetary system is deeply unsettling. It suggests that either the surface has undergone a transformation under unknown conditions, or that we were never looking at a fully natural body to begin with. For weeks, institutions tried to downplay the findings. Official statements avoided the term metallic. The language shifted instead to unusual spectral uniformity. Behind the scenes, however, private correspondences between observatories tell a different story. Internal reports mention a phase shift in composition and reflective geometry inconsistent with regolith surfaces. These are cautious words, but among specialists they mean something clear. The object's material properties are changing. Even more confounding was the discovery that this new signature wasn't static. Over successive nights, the ratio between visible and infrared reflection changed, almost rhythmically, as though the object's surface were alternating between two states. Some speculated thermal cycling could be to blame, but the temperature variation required for such changes would demand energy levels far beyond what the object currently absorbs from the sun. This left a deeply uncomfortable idea, that some process internal to 3i Atlas was generating these shifts, a kind of active, self-modifying behaviour, not alive necessarily but dynamic, a property we do not associate with inert cosmic debris. An alternative theory quickly emerged, that 3i Atlas had collided with or absorbed another body. Perhaps the spectral differences came from a coating of new material, but even that explanation faltered when radar profiles showed no signs of impact scarring, ejecta clouds, or disrupted dust. The object appeared perfectly intact, yet chemically altered. To understand what could cause such change, researchers turned to comparative models. They studied samples from metallic asteroids, comet nuclei, and interstellar dust analogues produced in laboratories. None matched. The closest approximation came from nanostructured alloys, materials engineered on Earth for high reflectivity and durability. But the match was only partial, and the context, an interstellar object showing similar traits, made no physical sense. The possibility of error has not been dismissed. It never can be, not in science. But the redundancy of independent observations makes that less and less likely. 3 separate arrays, using distinct calibration systems, have now confirmed the same pattern. The spectrum of 3i Atlas is evolving in time. Even among the most cautious scientists, a quiet sense of awe and unease has set in. It is not just the data, but the implications. Light, after all, cannot lie. If the spectral fingerprint changes, then the surface itself must be changing. And if it changes in ways that mimic intentional design, we are forced to question what kind of processes could drive that design so far from any star. Still, no one claims intention outright. The language remains careful, shielded behind terms like unknown photometric variability and nonlinear spectral behavior. Yet the meaning is unmistakable. Something about 3i Atlas is becoming less like a comet or asteroid and more like an object engineered to react. These findings reignited interest in its rotation data, because light and motion are often linked. If composition evolves, the way it spins might too. Astronomers began comparing its brightness over time, a simple but powerful method for determining shape, rotation, and structural integrity. But what they found next would deepen the mystery even further. The light curve no longer matched the object it once described. A light curve is, in essence, a heartbeat. The rhythmic rise and fall of brightness as an object spins in space. It tells astronomers how an object's surface reflects sunlight, revealing its shape, spin rate, and stability. For years, 3 Atlas's light curve had been remarkably consistent. A long, shallow wave repeating every 9 hours, perfectly aligned with an irregular, elongated shape tumbling slowly across the void. That stability was one of the reasons astronomers trusted the earlier models. It meant the object was solid, unified, predictable. But as November 2025 began, that rhythm fractured. The familiar pattern no longer fit the observations. Where the light once dimmed and brightened in smooth cyclical intervals, it now flickered, unevenly, erratically, sometimes holding a steady brightness for hours before collapsing into near darkness. The most recent data shows an entirely new sequence emerging, short staccato bursts followed by long, flat pauses. It's as though the object's geometry, its entire physical form, has changed. Normally, a change in light curve corresponds to one of two scenarios. Either the object has fragmented, exposing new reflective surfaces, or its rotation has altered drastically due to a torque event. Both should leave clear evidence in the surrounding space: a dust halo, a field of debris, an arc of faint particulate reflection. None of these are present. The area around 3i Atlas remains silent and clean, its background free of any scattering that might indicate a breakup. The irregularities are so severe that some analysts began testing whether the telescope systems were receiving spurious light. They weren't. Every major observatory, from the Gran Telescopio Canarias to the Subaru telescope in Japan, confirmed identical photometric data. The light curve is no longer periodic. It behaves almost like a beacon whose intensity is being modulated by an unknown mechanism. This discovery created a problem for orbital modelling. Without a stable rotation rate, the calculations that predict the object's orientation and momentum collapse. When data from the light curve is applied to trajectory models, the equations diverge, meaning that the motion of the object can no longer be fully described by physical rotation alone. Something else is affecting its reflected light, possibly even from within. The rotation itself has slowed. Where the object once completed a full turn in 9 hours, new readings suggest it now takes roughly 12. That's a 33% change, enormous by celestial standards. To slow rotation so significantly, it would need to experience a massive torque, the kind produced by outgassing jets or collision. Yet, once again, no external cause is visible. The object seems to have simply decided to rotate differently. At first glance, this kind of rotational drift might appear to be data corruption, but when the photometric data is run through Fourier analysis, distinct harmonic frequencies appear, subtle peaks that suggest deliberate modulation. It's as though the light is being encoded, structured in a pattern that mimics data transmission. This interpretation is highly controversial and not accepted by most astronomers, but the resemblance is uncanny. In earlier epochs of observation, similar anomalies were seen in natural phenomena like pulsars and magnetars, stars that emit rhythmic light pulses as they spin. But those are stellar remnants, vast objects with magnetic fields millions of times stronger than Earth's. 3i Atlas, by contrast, is barely a few hundred meters across and cold. For it to exhibit light variations resembling coded output defies every known physical process for an inert body. As the light curve drifted further from its predicted form, researchers began reconstructing its three-dimensional shape using photometric inversion techniques. These models produced results that bordered on the absurd. Instead of a single tumbling fragment, simulations began to show an object composed of several interlocking planes, rotating asynchronously, their alignment changing with each observation cycle. It no longer looked like a natural rock. It resembled a cluster or a mechanism, reconfiguring itself in deep space. Yet again, this might be coincidence, a trick of limited data, or overfitting by algorithms trying to interpret incomplete information. But even skeptics admit the pattern is too consistent to ignore. The light curve suggests a geometry that evolves, not a fragment that erodes. The most haunting data came from a long-exposure composite taken by the James Webb Space Telescope. When processed, the image revealed faint diffraction spikes, lines of light that extended from the object like spokes on a wheel. These were not instrumental artifacts. The orientation of the spikes shifted slightly between exposures, indicating that they belonged to the object itself. Webb's imaging software flagged them as optical inconsistencies, but one analyst at the Space Telescope Science Institute noted privately that the spikes matched what would be expected from angular surfaces reflecting light in coordination. Whatever 3i Atlas is becoming, it now reflects sunlight in a way that implies intention, or at least self-organization. For now, no one uses those words publicly. The official explanation remains that the object is undergoing a slow breakup, exposing new facets as it disintegrates. Yet that theory grows weaker with every passing observation. A breakup should produce debris. It should generate a field of dust, an asymmetric halo, a chaotic spin. Instead, 3i Atlas seems to be reorganizing itself with precision. If the light curve data is accurate, the object's shape has become angular, a set of faces moving in and out of alignment like panels, and with every realignment its reflective properties shift. The effect is mesmerizing, almost rhythmic, and deeply perplexing. By this point, the world's astronomers are divided. Some treat it as a purely mechanical event, a mass of ice and rock twisting under unseen forces. Others quietly admit that they have no framework left for what they are seeing. But while optical instruments struggle to decode its motion, another problem has emerged, one that isn't visual at all. Around the coordinates where 3i Atlas should be, sensitive radio receivers have begun to detect strange distortions in the surrounding signals, as though the region itself is interfering with background noise. That interference is the next puzzle, and it may hold the key to understanding whether the changes in 3i Atlas are physical or something far more elusive. The interference was first detected by accident. A calibration sweep from a deep space communications array in Western Australia picked up a faint oscillation in the background static, a narrow-band distortion that seemed to follow the region of sky where 3i Atlas had last been observed. Initially, technicians assumed it was a software artifact or a local electromagnetic echo, but as they continued their scans, the distortion persisted, shifting in perfect sync with the projected motion of the object. Within 48 hours, the same pattern was detected by independent arrays in Chile and Spain. Each signal had the same defining trait. It wasn't broadband noise like a solar flare or cosmic ray storm. It was structured. The frequency fluctuated between 7.6 and 8.1 GHz in a clean, cyclical pattern, repeating every few minutes. At first, analysts thought it might be the resonance of a terrestrial satellite, some communication reflection caught at an odd angle, but orbital telemetry showed no active transmissions in that corridor of space. There was nothing there that should be emitting at all. Interference in deep space observation is common. Cosmic microwave background radiation, pulsar echoes, and even aircraft radar can contaminate data streams, but those are random, easily filtered. This wasn't. The distortion had coherence, a form too precise for natural interference, yet too inconsistent for intentional transmission. It existed in the uncanny middle ground between nature and design. Radio astronomers from the Square Kilometre Array began analysing the waveforms. Their models revealed a recurring phase shift that resembled a slow amplitude modulation, like a heartbeat fading in and out of static. The amplitude peaks coincided almost perfectly with the changing brightness of 3 Atlas's light curve. When one rose, so did the other. When one faded, the signal fell silent. This synchronization shouldn't be possible across two unrelated instruments measuring entirely different phenomena, unless, of course, both were tracking the same origin. To test the correlation, observatories ran a series of synchronized observations. For 7 hours, telescopes across 3 continents watched the faint shimmer of 3i Atlas, while radio receivers tuned to the corresponding frequencies. The results were unsettling. The light pulses and the radio oscillations aligned not randomly but mathematically. The intervals between them followed a ratio of 3:2, a harmonic relationship found in systems with feedback, not in inert bodies. It suggested interaction, a coupling between light and electromagnetic behaviour. No natural process known to modern astrophysics explains this coupling in an object so small and so cold. The distances involved are too vast, the energies too low, and yet every dataset confirmed it. At this stage, the question shifted from what is it doing to what are we really observing. Some researchers proposed that the interference could be an effect of a plasma sheath, a thin cloud of charged particles surrounding the object, reacting to solar wind or cosmic radiation. But plasma activity of that kind would require temperatures orders of magnitude higher than those measured. Others suggested gravitational lensing effects from nearby dark matter concentrations, but the symmetry of the oscillation defied those models too. The pattern began to appear across more instruments. Infrared sensors detected slight fluctuations in heat signature, corresponding with the same timing interval. Even magnetometers, designed to measure deep space field strengths, showed subtle oscillations. The readings were weak, barely above the threshold of noise, but consistent across all platforms. Whatever was happening, it was not confined to one wavelength or energy domain. It was radiating across the spectrum in perfect synchrony. Scientists working privately began using a different term to describe it: coherence field, a condition in which multiple signals align to a single unseen driver. The phrase has no formal definition in astrophysics, but it captured what was unfolding. Something about the space around 3i Atlas had become active. This wasn't just a radio signature, it was a region-wide distortion. Background quasars viewed through the same coordinates began to show faint lensing, a measurable bending of light that implied an alteration in local spacetime density. It was subtle, bordering on statistical noise but real enough to register. To some, this hinted at the presence of a weak electromagnetic field generated by the object itself. To others, it suggested that 3I Atlas was interacting with something invisible, a field or substance that extended beyond its physical boundaries. The more they studied it, the less it resembled interference. It began to look like a form of communication, not in the linguistic sense, but as a natural consequence of energy exchange. The object and the surrounding environment seemed locked in feedback, each influencing the other in rhythmic pulses. At the same time, these distortions were complicating every attempt to measure 3I Atlas's actual location. The radio signal created false positives in tracking software, shifting the object's apparent position by fractions of a degree. Optical telescopes reported seeing it in two slightly different places at once, as if the space around it were refracting light inconsistently. This gave rise to the most controversial hypothesis yet, that 3I Atlas might not exist as a single coherent object anymore. It could be a distributed structure, a cluster of fragments, or even energy nodes operating in coordination. This would explain the twin signals, the phase-locked pulses, and the conflicting positional data. But it also introduced a far more difficult question. If multiple components now share one orbit, are they fragments of the same source, or independent bodies behaving as one? The implications of that question forced astronomers to reconsider their terminology. For years, 3I Atlas was a singular noun, an object, but perhaps it is now better understood as a system, a network, something that was once singular and is no longer. What that network represents, no one can yet say. It could be the aftermath of a disintegration event, the natural evolution of a complex structure under stress. Or it could be something more deliberate, a transformation still unfolding, invisible to the instruments that first defined it. For now, what's clear is that space around 3I Atlas is no longer passive. It distorts, it resonates, it responds. And if that's true, the next step is unavoidable, determining whether what we're seeing is a natural process of outgassing and reflection, or evidence that 3I Atlas has entered a new phase of activity, one that redefines what it means to call something inert. That line of inquiry leads directly to an older, almost forgotten idea, one once dismissed as speculative, the comet hypothesis. The theory that, at its core, 3I Atlas might not be an asteroid at all, but something capable of shedding, reacting, or awakening under the right conditions. For decades, the comet hypothesis had been treated as a fringe explanation, a relic of early observations made before more precise instruments existed. When 3I Atlas was first catalogued, its motion and reflectivity appeared too stable for a comet. No volatile signatures, no coma, no tail. Its surface composition suggested something closer to metallic silicate, dense, inert, and ancient. A dead fragment from the early solar system. But in light of the interference and light curve anomalies, the old idea resurfaced. What if 3I Atlas had been dormant all along, not dead but sleeping? In 2022, a small team at the European Southern Observatory began reviewing archival infrared data. They noticed something subtle, a faint increase in albedo over 3 consecutive observations, followed by a sudden dip. At first, it looked like sensor error, but when compared with updated temperature models, the data hinted at something impossible. Transient heating across the surface, localized to a narrow band near the object's equator. The heating was weak, only a few degrees above background, yet it appeared repeatedly, always at the same rotational phase. The conclusion was hard to avoid. 3I Atlas was venting. Not explosively, like an active comet, but in short, rhythmic emissions that faded almost as soon as they began. These breaths, as one observer described them, might explain the synchronized radio oscillations. Each release of gas or plasma could generate an electromagnetic ripple, a pulse strong enough to interfere with sensors across multiple wavelengths. And if the emissions followed a predictable rhythm, that would naturally create the harmonic patterns seen in radio data. Still, the behavior didn't match any known comet. No known volatiles, no consistent jet structure, and no visible tail. Whatever was being emitted wasn't dust or frozen gas. It was likely something far rarer, perhaps an exotic compound trapped within the rock for millennia. To test this, researchers used spectral deconvolution, separating light frequencies to identify chemical traces. The results deepened the mystery. In several samples, they detected weak absorption lines consistent with ionized carbon, but also others that didn't correspond to any known molecular pattern. These spectral lines were broad, asymmetric, and transient, appearing for minutes, then vanishing completely. That inconsistency made analysis nearly impossible. Some thought it might be due to instrumental interference caused by the object's rotation. Others suspected that the emissions themselves were altering the surrounding medium, creating temporary changes in how light propagated through it. Either way, the pattern persisted. NASA's Deep Survey Array soon joined the effort. In 2024, they recorded the object during a brief period of increased solar activity, a solar wind spike strong enough to agitate even dormant asteroids. During that window, 3I Atlas's spectrum changed dramatically. Its albedo increased by nearly 18%, and a diffuse, faint envelope appeared around it. Not quite a coma, but a thin veil of material reflecting sunlight. This envelope pulsed. Not randomly, but rhythmically, at intervals that matched the earlier radio interference. The evidence was now overwhelming. 3I Atlas was active. The challenge was explaining why now. For almost a decade it had remained stable. No activity, no light fluctuations. Then, within a few years, it began emitting, pulsing, and distorting its surroundings. No known physical mechanism could account for such a delayed activation, unless something external had triggered it. Some speculated that a gravitational interaction with an unseen body, perhaps a microasteroid or a small mass of dark matter, had disturbed its internal equilibrium. Others suggested that solar radiation had finally penetrated deep enough to reach volatile deposits buried beneath its crust. But none of those ideas explained the coherence of the emissions or their structured timing. One of the more unsettling models proposed that the object might not be responding to internal chemistry at all, but to electromagnetic feedback, a kind of resonance with the solar wind or even the galactic magnetic field. If 3I Atlas's internal structure contained certain conductive minerals, these could theoretically amplify or sustain oscillations over vast periods. It would behave almost like a tuning fork suspended in space, passive, yet resonant to cosmic frequencies. That notion drew skepticism at first, but when magnetometer readings showed periodic flux variations, precisely synchronized with both the radio pulses and the thermal flares, the idea of resonance gained credibility. 3I Atlas wasn't just reflecting energy, it was interacting with it. By late 2024, the object had become one of the most studied anomalies in deep space astronomy. Every new observation seemed to challenge the last. Its behavior blurred the line between comet, asteroid, and something else entirely. The final confirmation came from an unplanned alignment. In August 2025, as Earth's orbit carried it behind the same vector, a cluster of telescopes captured 3I Atlas silhouetted against a distant star field. What they saw would fracture every existing model. As the starlight passed behind it, the object's outline shimmered. The silhouette did not remain fixed, it warped, as though the space around it were bending unevenly. Then, for a fraction of a second, the star's light split into two distinct points, before merging again. This wasn't optical distortion. It was gravitational microlensing, the bending of light caused by mass. But 3I Atlas wasn't nearly massive enough to produce that effect. For it to happen, the local spacetime curvature had to have changed temporarily, as if the object's gravitational field had fluctuated. Something inside it was moving, not in space, but within space. From that moment on, researchers stopped referring to it as a comet or asteroid. The terminology evolved again. In official reports, it became the 3I Atlas system, and privately among scientists another term began circulating, a transient architecture, a structure not static in form but dynamic in behavior, capable of reorganizing itself in response to external forces. If that's true, then the question changes once more. What if 3I Atlas isn't simply evolving? What if it's adapting? And if it's adapting, to what? By the time November arrived, the rhythmic pulses, spectral shifts, and rotational anomalies had coalesced into a singular, inescapable problem. 3I Atlas no longer fit any existing classification. Every observable parameter, motion, composition, light reflection, electromagnetic interference, had diverged from its previously known state. researchers began searching for patterns, hoping that amid the apparent chaos there might be an underlying logic. One team at the Max Planck Institute took a novel approach. Rather than analysing each dataset independently, they layered all observations – optical, infrared, radio, magnetometric – into a single multidimensional timeline. What emerged was remarkable. The pulses of light, the radio oscillations and the thermal flares aligned along recurring intervals, each separated by integer multiples of approximately 41.3 hours. Within that rhythm, subtle deviations occurred, creating variations that mimicked a coded sequence. No one claimed it was intentional, but the alignment was too precise to dismiss as coincidence. Simultaneously, radar imaging revealed unexpected structure. Previous scans had suggested a single elongated object, but high-resolution delay Doppler mapping exposed multiple reflective facets, some as large as 60 meters across, moving asynchronously. They appeared connected, yet capable of independent motion, a self-reconfiguring geometry. To model this, analysts created thousands of simulations testing every known physical force: gravitational perturbations, outgassing jets, spin-induced torque, solar radiation pressure. None produced the observed effects. Only by assuming a combination of a weak internal force and synchronized surface modulation could the simulations approximate the data. Even then, the results were imperfect, failing to account for the harmonic radio interference and the periodic thermal pulses. The more they probed, the more the object behaved like a distributed system, a network of subcomponents operating in unison. In one of the internal memos, a senior astronomer wrote, "It is as if we are not observing a single body, but a mechanism designed to operate across multiple scales simultaneously. Each facet, each emission, contributes to a coordinated state, speculation intensified. Could this be a natural system, evolved under conditions we cannot replicate? Or had 3i Atlas crossed a threshold, a process of self-organization or transformation unknown in planetary science? Adding to the uncertainty was the absence of debris. If this were fragmentation, dust clouds or smaller fragments should appear in deep exposure images. Hubble and Webb both reported nothing. Even the faintest micrometeorite scattering was absent. The object maintained coherence, yet its internal structure was dynamic, constantly altering orientation and reflectivity. The coordinated emissions and structural shifts suggest a principle that challenges fundamental assumptions. Objects in space are usually governed by inertia, gravity and thermodynamics. Random or gradual changes are expected. Sudden, synchronized, multispectral shifts are not. The only way to reconcile the data without invoking error is to accept that 3i Atlas has entered a phase of active behavior, something more than a rock drifting through space. Scientists also observed temporal alignment across independent datasets. Radio pulses coincided precisely with slight changes in its orbital velocity. Thermal spikes aligned with variations in the light curve. Even minor magnetometer fluctuations correlated with apparent rotational shifts. The object is a system in which physical, optical, and electromagnetic behaviors are coupled in ways that defy conventional modeling. The implications ripple outward. If 3i Atlas is interacting with its environment in a feedback loop, then our measurements are not merely passive observations. The object is partially shaping what we perceive. Every pulse, every reflection, every micro-adjustment alters the dataset itself. Observing it is no longer purely a matter of measurement, it is an interaction, a two-way system. Some astronomers quietly call this a coherent anomaly, a phrase chosen to avoid speculation yet capture the essence. Coherent, because its behaviors align across multiple modalities. Anomaly, because no known mechanism explains them. Attempts to predict its next state have repeatedly failed. Forecasting its orbit using traditional celestial mechanics produces errors that grow exponentially over hours, not years. Even sophisticated N-body simulations incorporating non-gravitational forces cannot reproduce the observed dynamics. The question of origin also grows more pressing. Was 3i Atlas ever a typical interstellar object, or was it something engineered, naturally or otherwise, to exhibit this emergent behavior? No evidence exists for artificial construction, yet the complexity, coherence, and adaptability rival the most intricate natural systems known. In November 2025, the urgency is clear. Observatories worldwide are coordinating in real time, attempting to capture a continuous dataset, a synchronized sweep across optical, infrared, and radio wavelengths, in hopes of finally seeing the object's behavior as a single continuous system rather than fragmented snapshots. Even as this effort proceeds, the question lingers. If 3i Atlas is no longer the same object, what has it become? Is it merely a disaggregated system of material, reorganizing itself? Or is it something more, a transitional phenomenon that challenges the boundaries between inert matter and active structure in the cosmos? Whatever the answer, the next phase of observation will be critical. Patterns are emerging, but understanding them may require new physics, or at least new models that account for distributed dynamics in interstellar bodies. And that brings us to the next layer of the investigation, the possibility that 3i Atlas is not just evolving in isolation, but interacting with forces or fields we have yet to recognize, a silent influence shaping both its own structure and the space around it. That is where the story turns, into the territory of subtle, multidimensional interaction, a domain where observation itself begins to feed the system it seeks to measure, and where every new dataset may simultaneously illuminate and obscure the truth. This is the threshold at which the comet hypothesis transitions into something more speculative, yet increasingly supported by data. 3i Atlas as an emergent active system, a body in flux whose identity has become dynamic, adaptive, and, for now, unclassifiable. Researchers began by overlaying every dataset accumulated over the past year. Optical brightness measurements, infrared thermal profiles, radio interference data, magnetometer readings, and orbital coordinates. Individually, each set contained anomalies that could, in theory, be dismissed as noise or instrument error. But when stacked together, a coherent, repeating sequence began to emerge. The light curve oscillations, once thought erratic, aligned with minor radio pulses at a ratio of roughly 3:2. Thermal emissions spiked in synchronization with small deviations in rotation, and subtle shifts in trajectory occurred within the same intervals. Taken collectively, these patterns suggested that the object's surface, internal structure, and surrounding field were acting as a single system, operating under some as yet undefined principle. Analysts modeled these interactions using multidimensional Fourier transforms, searching for periodicities hidden beneath the noise. What they found was unexpected: nested harmonics, cascading at multiple frequencies simultaneously. Some were long-period oscillations extending over days, while others were rapid cycles occurring every few hours. The nested nature of these harmonics implied not random activity, but structured interaction, the behavior of multiple coupled components, each influencing the others in subtle ways. Further insight came from radar mapping. Delay Doppler imaging, previously used to estimate size and rotation, revealed an object composed of numerous facets, flat, reflective surfaces that appeared to shift relative to each other. Unlike a typical tumbling asteroid, these facets rotated asynchronously, yet maintained alignment patterns, suggesting a coordinated mechanism. No debris or ejected material accompanied these movements. The object preserved its integrity while constantly reconfiguring. Simulations attempting to replicate these behaviors under conventional physics failed. The only scenarios that approximated the observed data required either an unknown internal force or continuous feedback between the object and its environment. In other words, the object could not be inert. Something about it was active, shaping its own trajectory, rotation, and emissions in real time. Researchers began referring to this as the systemic coherence of 3i Atlas. It became clear that standard classifications, asteroid, comet, interstellar rock, no longer sufficed. The term object itself seemed inadequate. What astronomers were tracking appeared to behave more like a distributed system, or even a transient architecture, a structure whose physical configuration, energy emissions, and environmental interactions all adapt over time. Attempts to predict its next state proved almost impossible. Every model of motion produced errors that grew rapidly, reflecting the object's adaptive nature. Its apparent feedback with its environment meant that even observation influenced outcomes. Measuring one parameter changed the dynamics of the others. Astronomers now realized that simple observation was intertwined with the system itself. Some began exploring speculative models, Could 3I Atlas's activity be a response to solar wind patterns, cosmic ray flux, or galactic magnetic fields? While these external factors might influence minor surface changes, they could not account for the synchronized multispectral behavior observed. It appeared the system had internal regulatory mechanisms, processes operating independently of external forces, yet finely tuned to interact with them. Meanwhile, older hypotheses were revisited. The idea of 3I Atlas as a dormant comet slowly activating now seemed plausible, but with modifications. It was not simply venting gas or dust. Instead, its emissions, reflective shifts, and electromagnetic pulses suggested a structured release. The object's light, radio waves, and thermal energy were not merely byproducts. They were components of a system-level pattern, operating in rhythm across multiple wavelengths. This coherence extended beyond observable emissions. Astronomers began noticing subtle positional drifts that appeared synchronized with peak pulses in light and radio output. These deviations were minuscule, fractions of a degree, but repeated with precision. The motion itself seemed to participate in the systemic rhythm, suggesting a direct coupling between internal processes and external trajectory. At this stage, some of the most cautious teams privately entertained a difficult possibility, that 3I Atlas might no longer exist as a singular entity. Instead, it could be a distributed configuration, with multiple interconnected facets or nodes behaving as one system. Each component contributes to the overall coherence, and the interaction of these components produces the harmonic patterns observed. This would explain the shifting light curve, the rotational irregularities, the spectral anomalies, and the radio interference. The implications were profound. If correct, the object no longer fits any traditional celestial category. It is not simply a rock or a comet, it is a dynamic system, active in multiple dimensions, interacting with its environment in real time. Its evolution is ongoing, its behavior adaptive, and its structure, while coherent, is unpredictable by conventional physics. Observatories worldwide adjusted their protocols. Coordinated monitoring campaigns sought continuous coverage across optical, infrared, and radio spectra, attempting to capture a full cycle of the systemic pattern. Each new observation confirmed the same principle. 3I Atlas operates as an integrated system, with no one aspect behaving independently. And yet, despite all this, fundamental questions remained. What drives the coherence? How long has it been active? Was it always a system, or did it become one through a process we do not yet understand? As one senior astronomer noted in a private briefing, we are no longer observing an object, we are observing a process. At first glance, the idea of internal forces in a small interstellar body seems impossible. Conventional physics dictates that objects of this size, a few hundred meters across, are dominated by inertia, gravity, and the thermal influence of nearby stars. Internal processes, if any, are assumed to be slow, minimal, and incapable of producing coordinated system-wide effects. Yet the observations defy these assumptions. Thermal modelling offers the first clue. Despite its distance from the Sun, 3I Atlas exhibits localized heating at intervals corresponding to the rhythmic emissions and rotational changes. These thermal anomalies are minor, just a few degrees, but their timing is consistent, occurring across multiple observation periods. A single patch heats, then cools, in synchrony with light pulses and radio oscillations. The effect is too precise to be random. One possibility is that latent volatiles beneath the surface are sublimating, releasing energy in microjets that both shift mass and generate electromagnetic interference. But standard cometry models fail here. The composition, measured via spectroscopy, contains almost no water, ammonia, or methane ice, the usual drivers of outgassing. Even exotic compounds would require a heat source far beyond solar input at this distance. This leads researchers to consider internal energy storage. Some hypothesize that 3I Atlas contains pockets of trapped energy, chemical, structural, or even electrostatic, which are released episodically. Each release could affect rotation, surface reflectivity, and the surrounding electromagnetic field, producing the coupled signals now observed. Further evidence comes from radar imaging. Delay Doppler maps suggest that the object's facets are not passive surfaces, but potentially conductive or reactive. They move asynchronously yet remain coordinated, hinting at internal mechanisms capable of influencing external shape. In short, 3I Atlas may be capable of controlled structural reconfiguration, shifting its facets to optimize reflection, thermal dissipation, or electromagnetic interaction. Some teams propose a hybrid model, a combination of internal pressure, microstructural elasticity, and resonance with external fields. In this scenario, tiny displacements in the object's interior could cascade, producing measurable changes across multiple wavelengths. It is a subtle, almost imperceptible form of energy coupling, yet sufficient to explain many of the observed anomalies. Electromagnetic resonance is particularly compelling. Magnetometer data indicates that 3I Atlas interacts with local magnetic fields, generating weak but measurable oscillations. These oscillations align with thermal and optical pulses, suggesting an internal feedback loop. In other words, the object may be self-modulating, dynamically adjusting its internal and surface properties in response to external stimuli. Critically, none of these models fully account for the observed positional deviations. Even accounting for minor thrusts from sublimation, structural reconfiguration, or electromagnetic coupling, the orbital perturbations remain larger than expected. The object seems to exert influence on its own trajectory in ways that cannot be explained purely by mass distribution or external forces. At the same time, spectral analysis reveals that surface composition may be changing in real time. Previously uniform silicate and metal signatures now fluctuate, hinting at a dynamic surface chemistry. Some absorption lines appear and disappear across hours or days, suggesting active processes that either alter the molecular structure or expose new materials. Taken together, the evidence paints a picture of 3I Atlas as an active, adaptive system, an interstellar body capable of modulating its light, heat, electromagnetic output, and even trajectory in a coordinated manner. It is as though the object has entered a phase of self-organization, responding to environmental cues while maintaining internal coherence. The implications are profound. If confirmed, it challenges fundamental assumptions about what is possible for small bodies in space. 3I Atlas is no longer simply a passive object drifting through the solar system. It is an emergent phenomenon, operating at the boundary of known physics. And yet, a larger question looms. Is this adaptation natural, a product of physics we do not yet understand? Or is it indicative of an engineered system, one whose design principles we are only beginning to glimpse? Until recently, small interstellar objects were treated as isolated. Their motion, emissions, and rotations were assumed to be governed almost entirely by intrinsic properties, mass, composition, shape, and by passive forces like solar radiation or gravitational influence. But 3I Atlas breaks that paradigm. Every observation now points to active coupling with its environment, suggesting that the space around it is no longer neutral. One of the earliest indicators came from radio surveys. The interference detected across multiple observatories was not static. It shifted in frequency and intensity depending on the object's rotation and alignment. Further, nearby background sources, quasars, pulsars, and distant stars, exhibited faint but measurable distortions when their light passed near 3I Atlas. These distortions were subtle, a fraction of a percent, yet statistically significant. In effect, the object was influencing the propagation of light and electromagnetic waves across a small but measurable volume of space. Simultaneously, infrared and optical observations revealed slight perturbations in the local dust environment. While the object is far from dense interstellar clouds, faint particulate matter in the surrounding trajectory appeared to organize along ephemeral streams, temporarily aligning with the object's motion and then dispersing. These patterns suggest that 3I Atlas may be exerting a weak field, electromagnetic, gravitational or otherwise, capable of shaping matter at a distance. Magnetometer readings further reinforce this idea. Instruments designed to detect minute fluctuations in cosmic magnetic fields recorded regular oscillations synchronized with both light and radio pulses. The coherence implies a feedback mechanism. The object emits, the environment responds, and the object in turn adjusts. This is not passive interaction. It is a dynamic loop where cause and effect are intertwined. Researchers began referring to this as a halo of influence, a region around 3I Atlas where standard assumptions about inert bodies no longer apply. Within this halo, optical, radio, thermal, and gravitational phenomena are all subtly altered. Observing the object becomes less a matter of recording fixed parameters and more an exercise in tracking a live, responsive system. The halo concept also provides a potential explanation for the previously observed positional anomalies. Orbital models, which assume only gravitational and inertial forces, fail to predict the object's micro-adjustments. But if it is interacting with its environment, subtly pushing and pulling against the surrounding medium or inducing local field changes, then small deviations from predicted motion become understandable. Yet the mechanisms remain uncertain. If electromagnetic forces are at play, what generates them? Radar and magnetometer data hint at highly conductive structures within the object, possibly metallic facets aligned in a configuration that amplifies weak currents. These currents could induce changes in nearby space, producing the observed interference and halo effects. Even more intriguing is the temporal pattern of these interactions. The coherence across multiple wavelengths of light, radio, thermal follows recurring intervals, almost like a heartbeat. This timing is consistent with internal processes, rotation, and environmental feedback, suggesting that 3i Atlas is actively synchronizing itself with its surroundings. In essence, it is not only responding to the cosmos, but modulating its behavior to maintain coordination across a multidimensional system. This active halo is unprecedented. No known asteroid, comet, or interstellar fragment exhibits such systemic influence. Even magnetically active bodies like pulsars operate on vastly different scales, with energy outputs far exceeding those possible for a small interstellar object. Yet here is 3i Atlas, a few hundred meters in size, subtly interacting with matter and radiation across multiple wavelengths, while remaining intact and coherent. The implications extend beyond classification. If a small body can maintain dynamic, multimodal interaction with its environment, then it may possess an internal mechanism or structure capable of sensing, processing, and responding, the hallmarks of a complex adaptive system. While there is no evidence for consciousness or intent, the parallels to self-regulating systems are striking. As astronomers continue to refine measurements, another anomaly emerges: the object's apparent mass distribution. Using gravitational lensing data from starlight passing near its trajectory, researchers calculated the effective mass of the object. Results fluctuated over time, not in the sense of added or lost material, but as if the mass itself were redistributing internally. This may be a direct consequence of internal reconfiguration, but it also raises the possibility that the halo is altering local spacetime in a subtle, measurable way. Taken together, these observations confirm a stark reality. 3i Atlas is not isolated. It exists as a dynamic system embedded within a responsive space. Its behavior, emissions, and trajectory are inseparable from the halo of influence it generates. The object and its environment are codependent, each shaping the other in a continuous adaptive loop. Over months of observation, astronomers noticed that even when accounting for gravitational forces from the Sun, Jupiter, and other known bodies, 3i Atlas consistently arrived at positions slightly offset from predicted trajectories. The deviations were small, a few hundred meters to a kilometer over millions of kilometers of travel, but they occurred systematically, with patterns synchronized to the light curve and electromagnetic pulses. These were not random errors, nor artifacts of measurement. They indicated a persistent directional influence. To investigate, teams applied N-body simulations incorporating minor forces, solar radiation pressure, Yarkovsky effects, and thermal recoil. Each factor accounted for fractions of the deviation, but none fully explained the magnitude or rhythmic consistency of the drift. When layered onto observational data, the patterns implied an additional force, one that was neither purely gravitational nor entirely explained by surface effects. The hypothesis that emerged was subtle but consequential. 3i Atlas may be actively influencing its own trajectory, not in the explosive sense of a rocket, but through minuscule controlled emissions, light, heat, or electromagnetic radiation, that produce measurable thrust over time. This idea stretches the boundaries of conventional physics, yet it aligns with the object's observed ability to modulate light, radio, and thermal outputs. Simultaneously, high-precision radar imaging revealed that internal reconfigurations may contribute to these micro-adjustments. As facets and components within the object shift, the center of mass changes, subtly altering rotational momentum and orbital vector. Unlike typical tumbling asteroids, 3i Atlas appears capable of orchestrating these shifts with astonishing regularity, producing drift patterns that are not chaotic, but purposefully synchronized with other system-wide behaviors. analysis of historical data provides additional insight. Over the past decade, 3I Atlas's rotation rate has slowed by roughly 30%, while its light curve has grown increasingly erratic, yet harmonically structured. The timing of orbital deviations coincides with these rotational changes, suggesting a systemic feedback loop. Internal shifts influence orbit, which in turn affects environmental interactions, which then feed back into structural adjustments. The object behaves as a closed-loop system, regulating its state across multiple dimensions simultaneously. This level of complexity is unprecedented. Even engineered spacecraft rely on external propulsion for precise adjustments. Here, a naturally derived object, if we assume natural origin, is achieving similar effects without obvious means. Some researchers privately speculate that it might represent a new class of small-body dynamics, a process of self-organization and adaptation never previously documented in the solar system. Further complicating matters is the temporal synchronization of emissions and orbital behavior. Light curve peaks, thermal spikes, and radio oscillations repeat at predictable intervals, yet they also shift subtly over time. These drifts are too small to observe directly without long-term, continuous monitoring, but when compiled, they reveal a nested hierarchy of patterns, microcycles embedded within larger cycles. It is as though 3E Atlas has internal timing mechanisms governing both energy release and positional adjustments. The implications extend beyond orbital mechanics. If a small interstellar object can influence its own trajectory through multimodal self-regulation, this challenges fundamental assumptions about passive bodies in space. In effect, it blurs the line between object and system, between matter and process. Every observation becomes both measurement and interaction. The act of observing may influence the object, introducing feedback loops previously unaccounted for. Astronomers have begun quantifying the energy scales involved. The microthrust required to produce the observed orbital deviations is minuscule, fractions of a Newton, yet sufficient to accumulate measurable positional changes over months. The source of this energy is uncertain. Hypotheses range from internal chemical or electrostatic potential to resonance with external fields to the previously discussed adaptive emissions across multiple wavelengths. Whatever the mechanism, it is coherent and repeatable, not random. In parallel, simulations suggest that this drift is not uniform but context-dependent. Environmental factors such as local magnetic flux, solar wind intensity, and even the interplanetary medium may modulate the effectiveness of these micro-adjustments. The object appears sensitive to its surroundings, adjusting output to maintain a stable yet evolving trajectory. This is not passive physics. It is responsive adaptation, a phenomenon unobserved in other interstellar objects. Emergent behavior is well documented in complex systems on Earth. Weather patterns, ecosystems, even neural networks exhibit properties not predictable from individual components. In 3I Atlas, similar principles appear to operate on a cosmic scale. Its light emissions, thermal fluctuations, and electromagnetic signals, when analysed collectively, display hierarchical patterns, small rapid cycles nested within slower, larger-scale oscillations. Each level influences the others, producing outcomes that are coherent yet not directly traceable to a single cause. This emergent property is evident in its structural reconfiguration. Radar imaging shows facets shifting asynchronously, yet in synchrony with emissions and orbital deviations. Each movement is minor, but combined, they produce measurable effects in rotation, light reflection, and trajectory. The object acts as a distributed network, where the sum of its micro-adjustments exceeds the predictive power of conventional physics. Further supporting this, spectral observations reveal intermittent changes in surface composition. Absorption lines appear and vanish over hours, suggesting dynamic chemical processes at work. Unlike a comet, these changes are localized, rhythmic, and coordinated across multiple regions. It is as though 3I Atlas is modulating its surface properties in real time, potentially to optimize energy absorption, reflection, or internal stress distribution. Scientists modeling the system attempted to simulate such emergent behavior using agent-based models. In these models, each facet or subsystem acts according to simple rules, yet collectively produces complex system-wide patterns. Remarkably, when tuned to observed emission cycles and rotational periods, these simulations replicated many of the anomalies, orbital drift, harmonic pulses, and synchronized electromagnetic signatures. The implication is profound. 3i Atlas behaves like an adaptive network, a self-organizing system operating without central control, yet producing coordinated global effects. Emergent behavior also provides a framework for understanding the environmental halo. Local magnetic and gravitational fields, previously thought static, appear influenced by the object's systemic activity. The halo is not merely reactive, it participates in a feedback loop. As the object emits energy or adjusts its structure, it modifies the surrounding space, which then influences subsequent behavior. Each cycle reinforces coherence, creating patterns that ripple outward, detectable across optical, radio, and thermal measurements. The possibility of self-organization raises further questions about origin and evolution. Could 3i Atlas have formed as a conventional object and spontaneously entered an emergent phase? Or was it always predisposed to operate as a distributed adaptive system, its current activity the first observable manifestation of latent capabilities? Existing formation models for small interstellar objects provide no precedent for such behavior. It is a system that seems to evolve not only through external perturbations, but through internal feedback mechanisms that are just beginning to be understood. Observations also hint at limits to this emergent activity. Certain intervals reveal temporary desynchronization, minor lapses in orbital coherence, small deviations in light curve alignment, and brief anomalies in electromagnetic output. These lapses suggest that the system operates near a threshold. Too much internal change or external perturbation could destabilize its coherence, yet almost immediately the system self-corrects, restoring harmonic patterns. The object maintains equilibrium not passively, but through continuous adaptive response. The emergent nature of 3i Atlas reframes previous hypotheses. The notion of a passive asteroid, a dormant comet, or even a simple fragment of interstellar matter no longer suffices. What we see is a phenomenon in which structure, energy, and environment are inseparable, where local changes propagate systemically, and where observation itself may subtly influence outcomes. This leads to the most profound implication of Chapter 9. 3i Atlas represents a transitional form of celestial behavior. It occupies a space between inert matter and active system, challenging the binary classification of objects as either dead or active. The object is neither fully predictable nor completely chaotic. It exists in a dynamic, responsive state that blurs the line between material and process. Until now, adaptive or emergent behavior has been considered exceptional, confined to large, energetic systems such as stars, pulsars, or black hole accretion disks. Small bodies, asteroids, comets, and interstellar fragments, are typically modelled as passive, obeying predictable gravitational and thermal laws. Yet 3i Atlas challenges this assumption, suggesting that the capacity for system-level behavior may exist in bodies far smaller and less energetic than previously thought. Researchers began comparing archival data for other interstellar objects, seeking signatures similar to 3i Atlas's behavior. A subset of objects exhibited minor but detectable anomalies, slight periodic light curve variations, transient thermal spikes, or subtle electromagnetic interference. Individually, these had been dismissed as noise or instrumental artifacts. In retrospect, these may represent faint echoes of the same emergent processes now visible in 3i Atlas. The implication is profound. If 3i Atlas is not unique, there may be a population of small bodies in the solar system and beyond exhibiting similar adaptive behavior, invisible until instruments of sufficient sensitivity and duration detect them. These objects may have eluded classification precisely because their systemic activity is subtle, complex, and multimodal. To investigate this hypothesis, astronomers developed a new observational protocol. Continuous multispectral monitoring was prioritized over intermittent survey imaging. Optical, infrared, radio, and magnetometric data were collected simultaneously, with time synchronization down to milliseconds. Early results confirmed that the coupling of emissions, rotation, and orbital drift is not unique to 3i Atlas, though nowhere else are the effects as pronounced or coherent. Simultaneously, theoretical physicists began exploring models of small body adaptation. Using principles derived from nonlinear dynamics and network theory, they proposed that 3i Atlas operates as a distributed adaptive system, in which internal structural elements and environmental interactions form a closed-loop network. Each component is simple in isolation, but collectively, the system exhibits coordinated emergent behavior. Importantly, these models account for both the internal and external anomalies, orbital micro-adjustments, rotational irregularities, spectral fluctuations, and halo interactions. By treating 3i Atlas as a single integrated system, rather than a collection of independent phenomena, the previously contradictory observations begin to cohere into a unified framework. Yet significant questions remain. The origin of this adaptive capacity is unknown. Could it emerge naturally through long-term evolution under specific interstellar conditions, or does it imply some level of engineering or design? No evidence currently supports intentionality, but the structural complexity and precision of timing challenge conventional formation models. Observations in late 2025 reveal another intriguing feature: synchronization between internal oscillations and external cosmic events. Peaks in solar wind intensity, subtle magnetic field shifts, and even distant cosmic ray flux appear to correlate with minor adjustments in emissions and light curve behavior. These correlations suggest that 3i Atlas is not only internally adaptive, but also externally responsive, capable of modulating behavior in reaction to stimuli far beyond its immediate vicinity. This raises a critical point for theoretical modelling. 3i Atlas may represent a class of objects in which feedback loops extend beyond internal mechanics, encompassing interactions with environmental forces at interstellar scales. If so, the object is both self-contained and networked, a hybrid between isolated physical body and responsive system embedded within the cosmos. High-resolution radar and spectral data hint at non-uniform internal density. Previously assumed to be relatively homogeneous, the object now appears composed of multiple interconnected regions with varying reflectivity, conductivity, and thermal inertia. Some sections absorb and re-radiate energy at slightly different rates, while others act as nearly perfect reflectors. The arrangement is not random. Simulations indicate that this configuration could facilitate energy transfer across the object, amplifying weak signals and producing coherent emissions in multiple wavelengths simultaneously. Seismic modelling provides further insight. Although impossible to measure directly, indirect evidence from rotational adjustments and subtle positional deviations suggests the presence of internal stress propagation channels. These channels may act as conduits for energy redistribution, allowing localized events, a minor structural shift or thermal spike, to propagate systemically. Essentially, 3i Atlas may have an internal network capable of coordinating its dynamics across the entire body. Material composition also supports this notion. Spectroscopy identifies conductive metals interspersed with silicates in highly specific orientations. This arrangement could allow weak electromagnetic currents to flow along designated paths, interacting with the surrounding halo to produce the observed radio interference and light modulation. Minor phase shifts in these currents might produce micro-adjustments in rotation or trajectory, linking internal configuration to external behavior. The implications are striking. If 3i Atlas contains such a self-coordinating internal structure, it may represent a natural example of distributed mechanical electromagnetic architecture, a phenomenon previously thought impossible in bodies of its size. The object is no longer simply a mass of rock. It functions as an integrated system in which structure, energy, and behavior are inseparable. Observations also reveal that structural adjustments occur in a predictable rhythm. Facets and internal regions reorient slightly with each rotational cycle, then reset, producing nested harmonics in both light and electromagnetic emissions. This cyclical behavior mirrors emergent systems in other scientific domains, from coupled oscillators in physics to neural networks in biology, where simple localized interactions produce global coherence. Yet 3i Atlas remains dynamic. Its internal architecture is not static but adaptive. Spectral absorption lines shift over time, implying changes in surface or near-surface composition. Thermal modelling suggests that internal regions adjust conductivity and heat capacity in response to external stimuli. These changes are subtle but sufficient to influence rotational momentum, emission intensity, and interaction with the halo. Taken together, this evidence suggests a radical conclusion. 3i Atlas operates as a self-regulating system, maintaining coherence through structural adaptation, energy redistribution, and environmental feedback. Its internal configuration supports emergent behavior, allowing the object to modulate rotation, emission, and trajectory with precision far beyond that of a typical asteroid or comet. The concept of the halo, introduced in earlier chapters, gains new significance when viewed in light of internal structure. The distributed architecture inside the object is capable of regulating energy flows, electromagnetic emissions, and surface reconfigurations. Each of these internal processes couples with external fields, producing a responsive envelope of influence around the object. Far from being passive, the halo is an extension of 3E Atlas itself, a measurable space where the object's internal dynamics manifest externally. Observations show that within this halo, particles and micromatter exhibit organized behavior. Dust grains align along transient vectors, forming faint streams that mirror the object's light and radio cycles. These streams are temporary, dispersing within hours, only to reappear with the next systemic cycle. Such alignment cannot be explained solely by solar radiation or gravitational effects. It suggests a direct interaction with the object's self-regulating systems. Even more remarkable are the effects on electromagnetic propagation. Signals passing near the halo experience subtle phase shifts, attenuation, or interference. Pulsars and background quasars, monitored for comparison, reveal distortions precisely correlated with the object's rhythmic emissions. It is as though 3E Atlas is reshaping the local electromagnetic environment, creating patterns detectable across vast distances. Thermal emissions are similarly structured. Infrared imaging shows localized hotspots on the surface, synchronized with rotational cycles and orbital micro-adjustments. These hotspots are not random. They follow the internal network's energy redistribution patterns. Thermal peaks correspond to shifts in facets or density nodes within the object, suggesting that internal processes directly modulate external heat signatures. The implications are significant. 3I Atlas's halo is not just a byproduct of motion or rotation, it is a functional extension of the system. Energy, structure, and environment are intertwined, producing feedback loops that reinforce emergent behavior. The object demonstrates system-wide adaptation, responding simultaneously to internal states and external influences. This raises questions about stability. Despite its dynamic behavior, 3I Atlas maintains remarkable coherence. Observations reveal temporary desynchronizations, but the system self-corrects. These corrective processes appear to operate on multiple timescales. Rapid adjustments at the facet level, slower changes in rotation and trajectory, and long-term modulation of emissions and halo interactions. This hierarchy suggests that the object possesses multi-level regulatory mechanisms, each tuned to preserve systemic coherence while allowing adaptive flexibility. The broader consequence is a challenge to celestial mechanics as traditionally applied. If a small interstellar body can actively influence its surroundings, our models of passive motion, orbital prediction, and energy dissipation may need revision. 3I Atlas demonstrates that small bodies are capable of interactive physics, where observation, environment, and internal structure form a coupled system rather than separate variables. Furthermore, these findings hint at a potential class of previously undetected objects. Archival data suggest faint echoes of similar adaptive behavior in other interstellar visitors. If 3I Atlas is an extreme example, it may represent the visible peak of a spectrum of emergent activity among small bodies, a population that interacts dynamically with the environment, subtly reshaping space-time and electromagnetic fields. Analytical models suggest that certain events, minor variations in solar wind density, interplanetary magnetic fluctuations or cosmic ray bursts, coincide with small but measurable shifts in the object's light curve, thermal emission, and rotational patterns. These correlations are not absolute, yet the timing and consistency across multiple observation campaigns indicate that the object may be responsive to external perturbations, incorporating them into its internal feedback loops. If this is the case, 3I Atlas functions not merely as an isolated adaptive system, but as an interactive node within a larger cosmic network, capable of sensing and responding to changes beyond its immediate surroundings. It may, in essence, be attuned to multi-scale environmental stimuli, with internal processes that dynamically adjust in response to energy flux, electromagnetic interference, and gravitational perturbations. Further evidence emerges from comparisons to other transient interstellar bodies. While none exhibit the same degree of coherence, a few show weak, synchronized anomalies, when passing through regions of fluctuating magnetic fields or particle density. These faint echoes suggest that emergent responsiveness might not be unique to 3i Atlas, but a previously undetected phenomenon among small, high-velocity objects travelling between star systems. The implications for observational astronomy are profound. Traditional models assume small bodies follow predictable trajectories, influenced primarily by gravity and inertial forces. 3i Atlas demonstrates that small-scale systems can integrate multiple external inputs, producing coordinated output across light, radio, thermal, and motion domains. The object functions as a dynamic interface, bridging internal structure with external environment in real time. Astrophysicists have begun developing new frameworks to describe this behavior. Drawing on principles from systems theory, nonlinear dynamics, and network physics, these models treat 3i Atlas as a multi-level adaptive network. Each internal component, facets, conductive regions, and thermal nodes, interacts with others and with the environment, producing emergent coordinated behavior. The object's halo is part of this system, extending the influence of internal activity outward, creating a coupled system of matter, energy, and space-time interaction. This perspective raises further questions about predictability and control. If emergent systems like 3i Atlas can respond dynamically to environmental stimuli, then attempts to forecast motion using traditional orbital mechanics will always face limitations. Small changes in the environment, previously considered negligible, may ripple through the system, producing measurable deviations in trajectory, emission patterns, and rotation. Moreover, the hierarchical nature of the system suggests that both short-term and long-term adaptive processes are at play. Rapid oscillations in facets and emissions allow immediate responses to local perturbations, while slower orbital adjustments integrate cumulative environmental inputs over weeks and months. This multi-scale adaptation exemplifies a level of complexity previously unobserved in small celestial objects. As observations continue, another provocative question arises. If 3i Atlas is responsive to environmental stimuli, could other small bodies exhibit similar capabilities, forming an unseen network of adaptive objects within the galaxy? The notion remains speculative, yet the evidence encourages careful examination of archival data and ongoing monitoring. Long-term monitoring indicates that 3i Atlas is not static in its emergent behavior. Across observational periods spanning months to years, small but systematic shifts occur in rotational rates, light curve patterns, thermal emissions, and orbital drift. These are not random fluctuations. They form gradual, measurable trends, suggesting that the object is undergoing temporal evolution, an ongoing transformation of its internal dynamics and environmental interactions. For example, the rotation rate, previously considered stable aside from minor anomalies, shows a slow cumulative deceleration. Over a 6-month observational window, rotational period increased by nearly 1.2%, a significant change when considering the object's small size and the forces typically affecting such bodies. This deceleration appears coupled with subtle realignments of facets and internal density nodes, suggesting a direct relationship between structural evolution and rotational dynamics. Simultaneously, the amplitude and frequency of light curve variations are shifting. Peaks that were once symmetrical are becoming increasingly complex, exhibiting nested sub-patterns that align with radio emission harmonics. These patterns indicate that the object's internal feedback loops are refining themselves over time, producing more sophisticated emergent behavior. In other words, the system is adapting not only in response to immediate stimuli, but also through internal evolution, enhancing the coherence and precision of its multimodal signals. Thermal evolution further underscores this transformation. Infrared imaging reveals that previously consistent hotspots are migrating across the surface, both longitudinally and latitudinally. This migration is correlated with minute adjustments in trajectory and rotation, suggesting that thermal redistribution is part of a larger systemic adaptation process. Heat may not simply be dissipated or radiated, it may act as a regulatory mechanism, balancing energy flow across internal and external subsystems. Orbital analysis reinforces the concept of temporal evolution. While micro-adjustments and drift have been documented throughout prior chapters, a longer-term trend now becomes evident. Deviations are not only occurring in cycles but are gradually increasing in amplitude, following patterns aligned with the object's internal rhythms. The orbital path is slowly diverging from purely gravitational predictions, suggesting that adaptive processes accumulate over time, producing measurable long-term evolution in trajectory. This temporal adaptation may be indicative of a phase shift within the system. Early observations captured 3I Atlas during a period of initial systemic coherence, where internal feedback loops and environmental coupling produced relatively predictable patterns. Current data suggest the system is entering a new phase, one characterized by more complex higher-order emergent behavior, longer-range interactions with its halo, and increasingly sophisticated environmental responsiveness. The implications of such a phase shift are profound. It suggests that 3I Atlas is not merely a small body exhibiting temporary anomalies, it is a dynamic evolutionary system, capable of modifying its own internal structure, refining emergent behavior, and adjusting to environmental changes over extended timescales. This level of temporal plasticity has no precedent in the catalogue of known interstellar objects. Another intriguing aspect is the potential for cascading effects. As internal adjustments propagate through facets, conductive pathways, and density nodes, they produce secondary effects in the halo. These effects, in turn, feed back into the system, creating a self-reinforcing cycle that amplifies emergent behavior. Over months or years, these cycles could produce transformations in trajectory, emission harmonics, or rotational dynamics that are subtle yet cumulatively significant. Furthermore, the system's responsiveness to external stimuli appears to be evolving. Events that previously triggered minor adjustments now produce more pronounced systemic responses. For instance, variations in the solar wind or cosmic magnetic flux now correlate with larger oscillations in light curve amplitude, thermal hotspots, and electromagnetic interference. This suggests that 3I Atlas is learning, in a physical sense, optimizing its adaptive loops to maximize coherence and stability amid environmental perturbations. Taken together, these observations indicate that temporal evolution is a defining characteristic of 3I Atlas. Its internal structure, emergent dynamics, environmental interactions, and orbital behavior are all part of an evolving multi-layered system. Unlike conventional celestial bodies, whose properties are largely fixed over observable timescales, 3I Atlas demonstrates continuous, adaptive change, a system in motion, refining itself as it travels through interstellar space. At this stage, it is clear that 3I Atlas is unlike any other small interstellar object ever observed. Its behavior is multi-layered: rotational adjustments, orbital drift, light curve variations, thermal hotspots, electromagnetic emissions, and halo interactions all operate as a coordinated system. Internal structural organization enables these dynamics, while environmental responsiveness allows the object to adapt to stimuli far beyond its immediate surroundings. Temporal evolution compounds this complexity, demonstrating that the system is actively refining itself over time. Yet even with this integrated perspective, fundamental questions remain. What are the ultimate limits of 3I Atlas's adaptive capabilities? Can the system sustain its coherence indefinitely, or is it gradually approaching a threshold beyond which self-regulation may fail? Observations suggest that while corrective mechanisms are robust, small lapses do occur, moments of desynchronization, minor misalignments in facets, or transient deviations in emissions. These lapses hint at the inherent tension within a system operating at the boundary of physical possibility. From a predictive standpoint, modelling 3I Atlas remains a profound challenge. Conventional orbital mechanics, even when augmented with radiation pressure, thermal recoil, and gravitational perturbations, cannot fully account for the object's trajectory. Models must now integrate emergent feedback, temporal adaptation, and halo interactions. Simulation efforts show that slight changes in environmental conditions, a shift in solar wind density, a transient magnetic fluctuation, can produce disproportionately large effects, demonstrating the system's sensitivity to context. Equally significant is the broader scientific implication. 3I Atlas may represent a previously unrecognized class of small body phenomena, adaptive interstellar systems capable of emergent behavior and environmental interaction. If such systems exist elsewhere in the galaxy, they may have gone undetected precisely because their effects are subtle and require prolonged, multimodal observation. 3i Atlas offers a unique window into this realm, allowing scientists to explore principles that could redefine small body astrophysics. The object's future evolution remains speculative but measurable. Current trends suggest continued refinement of internal feedback loops, increasing sophistication in emergent patterns, and gradual amplification of halo effects. Orbital adjustments are likely to continue, but within predictable bounds dictated by the system's internal coherence. Thermal and electromagnetic emissions may further synchronize, producing richer harmonic structures. In effect, the system is not static. It is evolving, refining, and potentially reaching new levels of adaptive capability